So on today's tutorial we are going to make an experiment. We are going to find out how much data we need to train a machine learning model. There is a huge misconception in machine learning which says that the more data you use to train a model, the better. And that is not true, that is false, because the more data you use to train a model means you are going to spend more time training the model. And it also means you are going to spend more time annotating the data and curating the data. So the more data you use to train a model is just going to make the entire process way more expensive. It's not about maximizing the amount of data you use to train a model, but it's actually the other way around. You want to minimize how much data you use to train a model. Obviously, you want to achieve a very good performance. You want to achieve a very good accuracy when you are training a machine learning model, but for a given threshold of performance, you want to minimize how much data you are using to train the model. Now, let me give you more details about the experiment we will be doing today. I have already prepared all the datasets you can see over here. Each one of these directories is a different dataset, and the difference between all of these different datasets is how much data we have in each one of them, right? We are going to train a machine learning model with each one of these datasets, and then we are going to compare their performances. We are going to train an object detector, so we are going to train a model in order to detect objects, and we are going to use YOLO V8. So we are going to train an object detector with YOLO V8, and the difference between each one of these datasets is how many images we have in each one of them. And for example, this one, which is called 10, it means we have exactly 10 images in this dataset. This one, which is called 50, means we have 50 images in this dataset. This one, which is called 100, means we have 100 images, and so on. Then we have these other datasets which are comprised of 200, 500, 1000, 2000, and 4000 images. Remember, we are going to train an object detector with each one of these datasets, and then we are going to compare their performances. So we are going to use YOLO V8 in order to train this object detector, and we are just going to use all the default parameters. As you can see over here, the only parameter we are going to specify is the number of epochs, which we are going to set in 20. So we are going to train each one of these object detectors for 20 epochs, and we are going to take the model we produced at the end of the training process, at the end of the 20 epochs, and then the only thing we're going to do is to compare the performances of all these models. So this is exactly the experiment we will be doing today. So this tutorial is about showing you this experiment, it's about showing you the results, but it's not really so much about showing you how to do all the training process, right? How to train an object detector using YOLO V8 on a custom dataset. No, this is only about showing you this experiment. If you want to know how I train this object detector, then I invite you to take a look at other of my previous videos where I show you the entire process of how to train an object detector using YOLO V8 on a custom dataset. And this previous video, oh my god, I show you absolutely every single detail which is involved in this process, from how to annotate the data, how to train the model, how to evaluate the performance of the model, and so on. So if you want to know how I train this model, how I train each one of these object detectors, I invite you to take a look at that video over there. But for now, let's continue. Now let me show you the data I used to train this model. We are going to train an object detector. In each one of these cases, we are going to train an object detector to detect ducks. So this is the data we will be using today. You can see we have many images of ducks, and this is the data we are going to use in order to train all these object detectors. In each one of these cases, you can see over here, in each one of these datasets, the only thing I did was sampling, to take a sample of the images you can see in this directory. So for example, in the dataset which is comprised of only 10 images, I took 10 images at random from this directory. Then for this other dataset which is comprised of 50 images, I took 50 images at random from this directory, and so on. So the only thing I did was taking this dataset and just taking a few images at random in order to generate each one of the datasets you can see over here, right? And this is a dataset I downloaded from the Google Open Images dataset version 7, which is an amazing dataset with a lot of images, a lot of categories, a lot of annotations, millions of annotations you can use in order to train your machine learning models. And if you want to know how I downloaded this data from the Google Open Images dataset version 7, I invite you to take a look at this other previous video where I show you the entire process of how to download an object detection dataset from the Google Open Images dataset version 7. This is an amazing video. I show you absolutely every single step of this process, but this previous video is not available in my YouTube channel, but is available in my Patreon, so it's available to all my Patreon supporters. This is all about the experiment we are going to do, about the data we are going to use. Let me tell you something else about the experiment. Remember, we are going to train each one of these object detectors for exactly 20 epochs. We're going to take the model we produce at the end of the training process, and we're going to compare the performance of this model, and we're going to compute the performance of this model on a test set which is comprised of 100 images. And this is very important. We are going to use always the same test set of 100 images. So we are going to change the datasets we use as training set, but as a test set we are always going to use exactly the same dataset of 100 images. This is very important. Please remember, although we are going to change the dataset we are going to use as a training set, the test set is always going to be the same. This is very important because otherwise the experiment doesn't make any sense whatsoever, right? So this was another thing which was very important. Let me show you a few examples. I'm going to open, for example, these two directories over here. The one that's comprised with 10 images and the one that's comprised with 50 images, and you can see that the data is already in the format we need in order to train a model with YOLO V8. And if I open this directory, which is images, I'm going to open images in each one of these directories. You can see that in this case the training set is comprised of 10 items and the test set is comprised of 100 items. Now, if I show you the other directory, the other dataset, you can see in this case the training set is comprised of 50 items, but the test set is also comprised of 100 items. Now I'm going to open the test set in each one of these datasets, and you can see that we have exactly the same images in each one of these test sets, right? Because we are going to use exactly the same 100 images in order to test the performance of each one of the object detectors we are going to use today. The only thing we are going to change is the training set, but the test set is going to be always the same. Please remember, this is very important, and otherwise the experiment doesn't make any sense, right? We need to use exactly the same test data in all cases. So this is exactly the experiment we will be doing today. And now let me show you the results, because remember, this video is not about showing you how I trained these object detectors, but this is only about showing you the experiment and the results and so on. So I'm going to take this script I have over here, and this script is going to take all the results from all the training process, from all these different datasets, and it's going to take all the data, and it's going to take all the performance, and it's just going to produce a few plots we are going to use in order to make this experiment, in order to analyze all the results from this experiment. You can see we have two plots over here. One of them is the mean average precision in the last epoch as a function of dataset size, and I'm talking about the mean average precision in the test set, right? And you can see we have a plot which has the mean average precision in the y-axis and the dataset size in the x-axis. And then we have also this other plot over here, which is the training time as a function of the dataset size. We have the training time in the y-axis and the dataset size in the x-axis. So let's get started analyzing this plot we have over here. You can see that the mean average precision, the performance, is increasing as we increase the dataset size, right? We start with a mean average precision of around 60%, and then in the last dataset with 4,000 images, we have a mean average precision of 91.1%. So the mean average precision increases as we increase the dataset size. But please notice that although we are always increasing the mirror precision, in some cases we are not really increasing that much, right? In some cases it's only a very small improvement, right? For example, from 50 images to 100 images, you can see that we have pretty much the same performance. We have pretty much the same mirror precision. And if I show you over here, for example, if I show you these 4 models over here, you can see that the mirror precision, although it's increasing with the dataset size, is not really increasing that much. For the dataset with 500 images, we have a mirror precision of around 86%. I'm looking at this number over here, so you can see this is 86%. And in the case of a dataset with 4,000 images, we have a 91%. So it's increasing, but it's only increasing a little. It's only like a very, very small improvement. But if we look at the training time as a function of dataset size, you can see in this case the training time is increasing exponentially, right? You can see that this is growing exponentially. And let me do exactly the same as before. I'm going to take these 4 models over here, and I'm going to compare the performance with these 4 training times over here, and you can see that although we have only a very small improvement in the mirror precision, we have a huge increase in the training time, right? If we take this model over here, the one we trained with 500 images and the one we trained with 4,000 images, if we take these 2 models, you can see that we are just improving the performance, we're just improving the mirror precision in something like a 0.05%, right? Something around a 0.05%, because in this case we have a 0.86 mirror precision, and in this case we have a 0.91 mirror precision. So it's a very small improvement of only 0.05%. But if we look at the execution time, at the training time, you can see that the training time increases by a factor of 7, right? If we take this value over here, which is 500 seconds, and if we compare with this other value over here, which is 3,500 seconds, you can see that it's increasing by a factor of 7. So it takes 7 times more time to train a model with 4,000 images than the time it takes to train a model with 500 images. We have a very small improvement in the mirror precision, but we have a huge increase in the training time. So that's the first conclusion we should take from looking at these plots. This is very important, because remember, it's not only about achieving the best performance, the highest performance, but you have to look at many other factors. And if you are taking much more time to train the model and you are not really gaining a lot of performance, you're only gaining like a very, very small performance, then maybe it doesn't make any sense, right? You will need to make a conclusion in each particular case if it makes sense or not. But I will say that in the most generic case, maybe it doesn't really make a lot of sense. Now let me show you another way to evaluate the performance of all these models, which is looking at some results, right? Remember from my previous videos, I always told you that yeah, the mirror precision is important and all these metrics are very important, but at the end of the day, the most important thing is to look how it performs with a few images, right? With a few samples, with a few videos. So I prepared this video over here. Let me show you. And in this video we have many ducks which are just doing nothing, or they are just like walking in the water, or actually they are swimming, or they are doing something. I'm not sure how this action is called, right? Because they are doing something, I don't know how this is called, but it doesn't matter. We are going to use this video, which has many ducks, in order to see how each one of these object detectors we trained over here, how each one of these models performs, right? So let me show you the results. This is a very important test. Always remember, yes, look at the mirror precision, look at all these numbers, but also take a look how it performs on a few videos, on a few images, because otherwise it doesn't make any sense. So this is each one of the videos I produced with all the results, and I'm just going to open each one of these videos one next to the other, so it's going to be much easier in order to evaluate all of them at the same time. So these are the results, and you can see that, for example, in this case, this is the video I produced with the model I trained with only 10 images. Then in this other case, this is the video I produced with the model I trained with 50 images. Then this is the video I produced with the model I trained with 100 images, and so on. These are all the results from all the models. And you can see that in these two cases, in the case of when I use the dataset of only 10 images and the dataset with 50 images, we are not really detecting anything at all. The model doesn't perform well at all. We are detecting nothing. We are not detecting any dog whatsoever. So this is the first thing we should notice. Then in this other case, in the model I trained with 100 images, you can see we are detecting something. It doesn't perform very well. We have many misdetections and it's not really very stable, so it doesn't work very well. But you can see that at the very least we are detecting something. And then for this other model with 200 images, it also performs okay. We have a few misdetections and so on, but it's okay. And the same happens for this other model with 500 images, with 1000 images. You can see it's okay, but it's not perfect. Then I will say this other model with 2000 images, it performs better. I will say I really like how it performs. And then this other one I trained with 4000 images, it also performs very good as well. So these are all the results from all the models, and there are many conclusions we can take from here. The first one is this situation we have over here, that we are not detecting any dog whatsoever with these two models we trained with 10 images and with 50 images. And if we go back to the performance plot, to this plot over here, you can see that for the model we trained with 10 images, we have a 60% mean average precision, and with the model we trained with 50 images, we have something like a 73% mean average precision. So if we look at the mean average precision on itself, we would say, oh, okay, it doesn't really perform that bad, right? It's like okay, it's like an okay performance. It's not perfect, but it's like an okay performance, 60%, 73%. But if we look at some very specific values, if we look at these videos, you can see that the 60% and the 73% doesn't really mean anything at all, because we are not detecting anything. We're detecting nothing whatsoever. So these numbers, the 60% and the 73%, doesn't really say a thing, doesn't mean anything. It's completely meaningless in this case. Right? This is a very important conclusion. This is one of the reasons why I always tell you, yes, look at the mean average precision, look at the accuracy, look at all these metrics, but also look at how it performs with a few images, with a few videos, because otherwise this may not be very relevant, right? This may be meaningless. And also a very important conclusion, that if we look at the video we produced with the model we trained with 100 images, we can see that it performs okay, right? Many misdetections, it's not stable at all, but it's like, okay, we're detecting something. At the very least, we're detecting something. And if we look at the mean average precision in these two cases, in the model we trained with 50 images and in the model we trained with 100 images, we can see that the mean average precision is pretty much the same. In both cases, we have something like a 73% mean average precision. So we have exactly the same mean average precision, but the performance is completely different, right? This is the video we produced with 50 images, and this is the video we produced with 100 images. So the performances are completely different, right? With 100 images, we are detecting something. At the very least, we are detecting something, and in the other case, we are not detecting anything whatsoever. So that's another very interesting conclusion. The mean average precision, it's important to take it into consideration, but also take many other things into consideration, because if you look at the mean average precision on itself, it doesn't say anything. And you can see this is a very good example. It doesn't say anything at all. So this is another very interesting conclusion. And now let's take a look at this other video again with all the results. And if I were to choose, if I were to select the best models based on this performance we have over here, I would say that the best models are these two. The one we produced with the model we trained with 2000 images, and the one we produced with the model with 4000 images. I will say in these two cases the detections are more stable, and we have the least amount of misdetections, right? We are detecting all the dogs and everything looks very stable. And if you ask me, I don't really see a huge difference between these two videos. I will say they perform pretty much the same. Now let's get back to these other plots. Now I'm going to focus on this one over here, which is the training time as a function of the dataset size. And now let's take a look at the training time of these two models we have over here. And you can see that for the model we trained with 4,000 images, we spend pretty much twice the time to train that the model we trained with 2,000 images. So both of them perform pretty much the same based on the example I show you, but this model took twice as long to train than the other one. So in this particular case, it seems it doesn't make any sense to train the model with more than 2,000 images because you are not really improving the performance that much and you are just wasting a lot of time, and therefore you are wasting a lot of money, right? So this is another very interesting conclusion from these results. So this is going to be pretty much all for this video. This is the experiment I wanted to show you in this tutorial. Let me know what you think about this video in the comments below, and let me know if you would like me to make other similar videos in the future with other type of experiments. I have other ideas of other experiments we could make in our tutorials, but let me know what you think about this video first in the comments below. So this is going to be all for this video. My name is Felipe, I'm a computer vision engineer, and see you on my next video.